Okay, good. And so here, that is something. So what we have learned on Tuesday, we learn how the LU factorizations. And so before this examples, the last 10 minutes, I show you one concrete examples how to do the LU decomposition of factorization. And you would have one homework about this today. Maybe I will also give you something, some questions about the linear algebra. I mentioned one fact about the here, the product of the lower triangular matrix is still a lower triangular matrix. Maybe there is some, I will ask you to prove this. And this is the LU factorization, and we derive the LU factorizations from the Gaussian eliminations procedure. And the things about the LU factorization is really simple, and we just go over the Gaussian eliminations procedure and then recording the ratios, the ratios information here, and that is the LU decompositions. And now let's compare the LU. So here we cannot stop here. After you get the LU factorizations, what you need to do is we really need to, the original purpose of this question is to solve the questions AX equals to B, although I haven't mentioned the A here. So here we have the AX equals to B, and then now we have already factorized the equations, the matrix into the LU factorizations. So now what you should do is to solve the, so first we need to solve the Ly equals to B, and then second we solve the Y equals to UX. And for here we get the Y, and then from the second step we get the X. And that's what we do here. We first do the LU factorization, and then we use the factorization to solve the linear system of the equation here. So this is how to solve the linear system of equations with the LU factorization. And now let us compare the LU factorizations method with the Gaussian eliminations method. We have already compared this a little bit at the very beginning. In this sessions, I just briefly mentioned that here. I briefly mentioned that the Gaussian eliminations require 2/3 and cubic operations. And then I briefly mentioned that, okay, if you get a LU factorization, then we can use the Balmer substitutions procedures to solve the linear system. And the total cost, computational cost here is just a 2n squared. So once students, yes, I haven't mentioned the things in detail, so I should mention some more details here. Why do we have Gaussian eliminations, 2/3 and cubic here? So I'm going to go back to the Gaussian elimination to take a look what operations we need in the Gaussian eliminations. So let's take a look at here. We have, let's go back to the Gaussian elimination and count the operations we need to do it. So first of all, let's take a look. So for each I, we do the step 2 to the step 4, right? And then for the step 5, this is the divisions, right? And so for I, a specific I, how many divisions do we do here? We have a minus I divisions, right? Because we need to do for j equals to I plus 1, and then to the end. And then so actually for the step 4, the whole step 4, we do divisions. Division, how many divisions we do it here? Divisions we do for one specific I, and then the divisions is n minus I divisions. And this is the count for the divisions we did here. And then how many, so if we perform the step 6, there is a subtraction here, and there is the multiplications here. So if you take a look at here, this is the RJI times the row EI, but actually we are doing, so how many, so we need to perform how many rows updates here. We need to perform n minus I update here, right? And then how many multiplication here? Multiplication. So first we know that we need to update n minus I row, and for each row there are n minus I plus 1 multiplications here. If you take a look at this example here, if you take a look at the, let me see, let's see, okay. For example, for I equals to 1, how many multiplications you do for the row 2? You do multiplications for each element here. So it should be the n minus I plus 1. And then for this one, you have the n minus I plus 1 as well. You have n multiplications. You have to multiply each element here, and then to do the row changes here. And what about this one? For this one, for the I equals to 2, because now this one is totally 0, and then what we need to do is to multiply these elements and then exclude the first one, right? So here, this is how many multiplications we do here. We have m minus I and then plus 1, and then that is the n minus 1 here, because the I equals 2 in the second round. So we have the n minus 1 multiplications for each row exchange here, row changes here. So that's how we count here. We have n minus I plus 1 for each row's changes here in the step 6. But here we have to go into this loop for n minus I time. So we have multiplication, such many multiplication here. And you would notice that we do the subtractions, the same amount of the subtractions as the amount of the multiplication here. So for each loop, we have the subtractions or the additions. We have n minus I and then n minus I plus 1. And this is for each I, we do such amount of the operations here. So if we want to count the total amount of the operations we did here, we need to sum up the I from 1 to n minus 1. So what we have here is, okay, if you do, okay, for the first one, we are going to do the sum I equals to 1 and then I minus 1, because we want to sum up all the operations here. And then for the divisions, we have n minus I, and then we have the multiplication, n minus I plus 1. Also the subtraction, n minus I plus 1. So I'm not going to do the calculations details here. You need to use some calculation knowledge to count the number here, to simplify the number here. So I would just write the final number here. If you want to know the details, and then you can go to the I believe I have already posted that the alternative textbooks on Canvas, and then you can take a look at the Canvas, the lecture notes I posted on the Canvas. And so here at the end, if you count all the total number here, you would get 2/3 and cubic, and then 3 halves, and then 7/6 n. And this number, the n is really big and like 1,000s and 10,000s. And then you will find the number here, the first number is the dominant one, and which means that this is the numbers praise an important role here. So we just focus on the biggest number, and then we say for the Gaussian elimination algorithms, we need O and O 2/3 n cubic operations here. So because this number, if the n is very big, and then this one is just a significant number here. So we just keep this number, and this is how we count the number in the algorithm. So if you go back to the LU operation, and then you will find out that, so let's go to the examples you can understand here. So you will see that we are going through one Gaussian elimination. So if you want to solve the linear system with the LU factorizations, you know that at the very beginning you will have one Gaussian eliminations computational cost here. So the first part, you will have the O 2/3 n cubic here. This is the LU factorizations part, and then you record the method here, and then there's not so much job compared to the n cubic here. You just need to record the information here, right? And then so there's not so much jobs compared to this computational cost. So this is the first part of the LU computation, and then after you get the LU computation, and then you would go to the solving this system, the linear system of the equation with the backward and forward process, and backward forward substitutions process, and then this costs you 2n² operations. But as I mentioned before, you will see this happens. Usually in mathematics, in engineering, the things is changing. It's not the matrix A, it's the input B. We have different inputs, and then we want to solve for the X, and then that's the engineering and mathematics. The usual case here, the A does not change a lot. So the benefits of using LU factorizations is that you have a lot of inputs and right-hand side here come in sequence, and then one by one, and then you need to solve for the x1, x2, x100, or sometimes x1000. And for this time, and then if you use the LU factorizations, you just need such, and you just need the initial LU factorization, and then you can solve for the system of the linear equations with the LU factorization. And for each time, you just need a 2n². So for example, we have 100 input here. And then so if you want to solve for 100x, and then we have such a computational cost here, 100 times the 2n². But compared to if you use the Gaussian eliminations each time, and then that would be 100 times the 2/3 n cubic. And now I will show you one concrete examples on the canvas on the Google Colab. So let's go to the Google Colab. Let me log in first. So I have already posted the codes on the canvas. You don't need to do anything about it, and then you just need to try it, but it is not homework. I just pause it, and if you are curious how the LU factorizations give you some benefits in the calculation, and then you can run the codes on the canvas. It's here, compare the Gaussian eliminations and LU factorizations. So first, usually we have a very big matrix, and then that's when we benefit we get some benefits from the LU factorization. So let's say, let's go to the very beginning here. this is the timer. I just count the time we use to calculate the solutions. So here it defines the Gaussian elimination procedures. We just need to give the input. It's the matrix here. And actually, we also, this matrix is the augmented matrix here, which means that that's the, what's that? That's the, here the inputs in the code is the augmented matrix with the coefficient here, and then this is the right-hand side. So we have, if this is the n by n matrix, and then this is the n by 1 vector, and then so this matrix should have n rows, and then times n plus 1 column. And this is the input for the code. And let's go to the next part to see what happens here. I'm going to define the n as the 500. This is a really big matrix, 500 by 500. And I'm going to use the package here to generate one symmetric positive definite matrix. Let's do it. Generate the positive definite matrix here, and I'm going to generate one random right-hand side, and then put them together to be my augmented matrix, and then I use functions defined above. That is the Gaussian elimination, so algorithm to solve this, and then let's count the time. Here is the timer start, and then end the timer, and then we print out the time. So you could see we need to wait for some seconds. That's bad. It's already 20 minutes, 20 seconds, 22 seconds. Okay, let's wait. Okay, 34 seconds, just for one input. So if you have more inputs, it's just like, if you have 10 inputs, it's approximately 340 seconds to solve for 10 inputs. It's approximately 6 minutes. So it doesn't make sense. You just have a 500 by 500 matrix. Why I said it doesn't make sense, because usually we can get this 10 inputs if you put the 10 inputs here and then 500 by 500 matrix into some package. They have the software there, and then it's so quick. It's just like 1 minute and then for 10 inputs. So let's see what happens here if we use the LU factorizations here. Actually, we have some package, and then it just have it. This is from the SciPy package, and then it would give you the LU factorization. And then after you get the LU factorization, and then you give the result, the LU factorization results to be the LU solve input, and then the LU solve will solve the linear system of the equations for you. But be careful here, pay attention to here. So you will see the time, this LU factorization here, if I just factorize the 500 by 500 matrix I have there, the A, and then let's take a look how much time do we need. It's so quick, it's just 0. It's like 0.015, but here, actually, if we code the LU factorizations code by ourselves using the for loops, and then we may need to take 34 seconds. But here in the package, it used some optimized method in the coding. They use the matrix instead of the matrix multiplication and some other optimized coding technique there. So it just takes the 0.015 seconds. But if you use the for loop and then updating each row there, and then to get the LU factorization, you need the 34 seconds. But let's see if we have multiple inputs And then how many we have, so let's say the LU factorization is just like 34 seconds if we need use the for loops coding. And if we get the LU factorization and then get the LU factorizations result here, and then as an input, and then this is the B vector is the random right-hand side here. We have 10 randoms right-hand side here, and then but so for the XI, and then we with the say coefficients matrix A here. So let's take a look how much time do we need here to solve for 10 different inputs. Oh, it's so great. So you can see the factorizations actually takes much more time than the LU solve here. We have 10 inputs here, but here we just have 0.006 seconds to solve for 10 inputs. And then it's so quick compared to if you need 34 seconds and then 10 times of the 34 seconds to solve with the Gaussian elimination. And this is the benefit of the LU factorizations here. And that's all the things about the Gaussian elimination and LU factorizations by so far. But actually we have some more theoretical things about the LU factorizations. And let's go back to the discussions there. Let's go back to there. So let's go back to here, and then we have one questions at the very beginning, and that question is that what kind of the matrix can have LU factorizations? And let's go scroll down. So we have a theorem here, and then it says if the Gaussian eliminations can be performed on this system of the matrix, and then with our row exchange, and then we can have this LU factorizations. So what does this kind of matrix look like, the A? So today I'm going to answer this question, and then this theorems, you should memorize that, and then maybe I would need to ask you to write down the theorems on your final exams. So the questions, we have some questions here, and then the question is, what kind of the matrix? What kind of matrix says A have LU factorizations? So there's one theorem about this, and then it's the if you take a look at the Hatter's textbook, it is the theorem 9.1, and it's the LU factorization. It tells you what kind of the matrices have such an factorizations. So this should be, so we have the requirement here, A is an n by n matrix, and then and this is the first requirement. It's a square matrix, and then it's leading matrices, leading principal submatrix. Submatrices A1 and then to the AN are all non-singular. And that's the requirement for the A, and that's it. And so for such an A, then A has LU factorizations. And the factorizations are unique. It's unique. It's unique. And then you could see this is a requirement for the A matrix. And let's see, one, I'm not going to prove this theorem. You can go to the Hatter's textbook to see to read the proof there. So let's see what does this mean, leading principal submatrix. So we already know what is non-singular, right? That means the determinant of, this means that the determinant the determinant of the AK is non-zero, is bigger than 0. It's a non-zero. And then for K equals to 1 to the N, and this is the definitions of the non-singular, right? But what's the definition of the leading principal submatrix? So let's see. Leading principal submatrix, it means that, so let's take a look what we have here. So the A matrix, it looks like this, right? A11 and then A12, and then to the A1n and A21, A22 to the A2n. And all the way to the AN1, A1N2, and the ANN, right? So what is the leading submatrix, the leading principal submatrix? So for the A1, AK, so leading principal submatrix is defined in this way. Leading principal submatrix, and then it's defined in this way. The AK, this is the K leading principal submatrix. It is just the left upper part, the left upper square there. So left upper square there, square part here. And then it's the K by K part. And so here, which means that it is this leading principles submatrix is just the all the way to the, not the A1, and it's just the A1K. And then A2K, and then all the way to the AK1, AK2, and then AKK. So that's just the square parts on the left upper part. It's a square, and then it's on the left upper part in the original matrix, and it's a K by K. So let's say, let's get one example here, and then if we want to get the A2, that is the leading principal submatrix, and then with the subscript 2, and what does it look like? It is just the A11, A12, and then A21 and A22. And that's the definitions of this leading principal submatrix. And so now you can totally understand this theorem, right? So this is the square matrix A, and then it's leading principal submatrix, and we can just represent it with the AK, and then they are all non-singular, which means that the determinant of that left upper square part for each left upper square part, the determinants are non-zero, and then that's it. And we have that factorizations. And this is the LU factorization theorem. Let's see. There's one corollary here. The corollary is based on this theorem. And then let's see. So let's get to some concrete example here. And then one matrix we are familiar with is the symmetric positive definite. And does this kind of the symmetric positive definite matrix satisfy this criterion here? The criterion 1 and 2. So let's check. So there's a corollary here, and then it's also on the textbook. And it gives two concrete examples about the matrix A, which has LU factorizations. And so you have, so if matrix A has LU factorizations, if either the situation, the two situations below. So the first situation is the A is a symmetric positive definite definite matrix. And this is a situation one, and then if you have such a matrix, and then you have the LU factorization, and this is just one specific examples under the theorem one, and then there's another one concrete example, and then that is the A is the strictly diagonally positive dominant matrix. And this one is more easier to determine if it has a LU factorization, because this one is easy to check if it is a strictly diagonal dominant matrix. So let's go to take a look why the first case is correct. If we have the theorem 9.1, why the symmetric positive definite matrix satisfies such an criterion 2 here. The leading principal symmetrics are all non-singular. Actually, if you go to the textbooks, there's one theorem to help us to go from the corollary, go from the theorem to the corollary here, corollary 1 here. So that fact is the theorems, we have the theorems 8.1 here to help you transfer from the theorems 9.1 to the corollary 2 here, corollary 1 here. So what does the theorem 8.1 on the textbook say? Theorems 8.1 it says that if let A is a symmetric matrix, n by n matrix. Let A be this, and A is a positive definite matrix. It's a positive definite matrix. If and only if the determinant of the leading principles matrix is always, the determinant is always bigger than 0. It's a positive one for all the leading principles matrix. And this is the theorem 8.1 tells us. If this is a symmetric matrix, and then the A is positive definite if the determinant, if and only if the determinant of each leading principles matrix is positive. And because this one is positive, so it satisfies the criterion 2 here. The criterion 2 here. It only requires this one is non-zero, right? But now we have the positive one, and then it's better, right? So now we have the corollary 1, and then if A is a symmetric positive definite matrix, we have the LU factorizations here. And what about this? The second one, strictly diagonally dominant. And what does that mean? This one is really useful because you can check, it's easy to check if this one, a matrix satisfies such a criterion. But this is one of the 2 situations in the corollary, they are not equivalent. They are 2 separate situations here. So let's take a look at the second situation. What does the strictly diagonally dominant diagonally strictly dominant mean? So the definitions here, let's say we have a matrix A, and then it's still a n by n. But this time, it doesn't require the matrix is symmetric. You can see the criterion 1 here, the criterion here. We have a symmetric requirement here in the situation 1, but situation 2, we don't require a matrix to be symmetric. So let's see, what does it mean by strictly diagonally dominant? So we have a n by n matrix here. A is n by n matrix. is an M by M matrix. So with the entries, we have entries Aij here. Strictly diagonally dominant, it means that the diagonal elements and then it's bigger than the sum of the rest of the elements in the same row, and that's the definitions of the strictly diagonally dominant. So let's see. Let's double check whether this matrix is a strictly diagonally dominant. So let's say this is a 3, and then -1, and then this is the 2, and then this is the -1. So let's check if this one is the strictly diagonally dominant. So how do you check it? So you check one row by one row. So first, let's check the first row, and then the diagonal elements here is 3, right? And then you have 3, and then is it bigger than? So the question is it bigger than the sum of the rest of the elements on the same row? The rest of the element on the same row, but excluding this one. And then we take the absolute value and then sum them up. And this one is actually the diagonal one because we only need to sum up the -1. And then this one is just the 1, right? And we finish first row. And then let's take a look at the second row. The second row, we have the diagonal element here is set the 2, right? And let's check if the 2 is bigger than the sum of the rest of the element. Yes, it is. So this is the strictly diagonally dominant matrix. We check each row here. So I'm not going to give you another examples, and then you need to check if it is a strictly diagonally dominant matrix there. So let's say this is 2, 2, and then 2, 1, 3, and then 3, 1, 2. And then is this a diagonally dominant one? No, why? Because the 3 is smaller than 2 by 2 plus 2, right? And now let me change one thing. If I change the negative sign, is that a diagonally dominant? No, because we need to do the sum for the absolute value, not just the original value itself, right? So this one is not diagonally dominant. So this one is not, and then this one is the diagonally dominant. And so you could see that it's easy to check one row by one rows, and then just by the summations. And it's better than the positive definitions, because this one is easy to check, but usually the positive definite is more general situations. So that's 2 situations here. Why do we have a second corollary here? We have already finished the definitions of this one, and then, but why does this one satisfy the theorem 9.1 there? So I will not do the proof, but I will show you there's one theorem to help us to transfer the theorem 9.1 to the corollary. So there's one theorems on the textbooks is the 3.6 theorems, and then we, with that, the help of the 3.6 theorem, and then we got the corollary to conclusions. So what does the theorems 3.6 said? It says if A is strictly diagonally dominant, and then we have the A is non-singular. So because you would see if A is a strictly diagonally dominant, right? And it also means that if you take a look at the structure of A, And then you will see if A is a strictly diagonally dominant, which means that each AK, and this one, it also implies that each AK, that is the leading principles submatrix, is also strictly diagonally dominant, right? So here we have, so if one matrix is strictly diagonally dominant, and then we can take a look at the structure of A, and then it's easy to see that AK, the leading principles submatrix, is also strictly diagonally dominant. So with these theorems, the help of these theorems 3.6, we know that for each leading principles submatrix, they are non-singular. So this satisfies what we have in the criterions, in the criterion of the theorem 9.1. So we have such two corollary here with the help of the theorem we mentioned before in the textbooks. And that's two situations we have here. Now I have already answered all the questions about the LU factorizations. When do we have LU factorizations for the matrix? But actually, for general non-singular matrix, we do have LU factorizations, but up to permutations. Because if you take a look, so the conclusion is that if A is just a non-singular matrix, and then we have if, and then with one proper permutations matrix, and then we have PU, and then that is a PA, which means that the P here is acting the role of row exchange here. And then after the row exchange, and then we don't need to perform any row exchange during the Gaussian eliminations. Then, so for this results, we can perform the LU factorizations on it. Because for each non-singular matrix, you can perform the Gaussian eliminations, right? But you can perform the row exchange first, and then after the row exchange, and then you can perform the Gaussian eliminations without row exchange. So this is the results after the row exchange. This one represents the row exchange here, the P. And so I'm not going to into some details here, how to write out the permutations matrix. You can go to the textbook to take a look. The permutations matrix, it just means you are exchanging some rows here. Reorganize the rows here, and then after some row exchange, you get one result, and then that result you don't need to perform any row exchange during the Gaussian elimination. And that's the very original LU factorizations theorem we have in the very beginning. So that is up to one permutations, and then the A, the non-singular matrix, it has LU factorization, and that's all the theoretical aspects about the LU factorizations. Any question about the LU factorizations? All the things. So I will specify which theorem or which corollary you need to memorize for the final exam. And I will also post the type one, the well typing ones, and then you can memorize it. And this is the LU factorizations. Some people they don't like LU factorizations because you need to go through the Gaussian eliminations, right? And some people just say, okay, let's reduce the cost of the LU factorization into half. You have 2/3 n cubic, right? Let's reduce to 1/2 of the computational cost. So that's the Cholesky factorization, reduce the cost of factorizations into half of the cost. And that's the Cholesky factorizations. So the Cholesky theorems, Cholesky factorizations here. But here in the Cholesky factorizations, we don't have the general things. So if you take a look at the corollary here, and then the matrix could be not symmetric, it could be just strictly diagonally dominant. But here in the Cholesky factorizations, actually we have strict requirements on the matrix A. So we require the A to be symmetric and then positive definite matrix. And so this one is better than the LU factorizations because we just need one matrix, and then that's the unique. Then there is a unique lower triangular matrix B. So what does it mean by lower triangular? It means that we only have elements in the lower left part. So we only have the lower left part here. Non-zero parts are all here, and then this part is 0. And so we have the unique lower triangular matrix B, and then we can write and there's one more things about the matrix here. With positive, we don't have any negative things in the entries, and then they are all positive entries, and in not the entries, just on the diagonal. It's on in its diagonal, and then such that the A can be the product of the B and then B transpose. So here, which means that we have positive entries here, and then it could not be, so if you have such an Cholesky factorizations, you have positive entries on the diagonal, and then they will not be negative. But you can have some negative things here below the diagonal. But here, they are all zeros. And this is the Cholesky factorization. And actually, the Cholesky factorization could be derived from the LU factorizations by this. So if you take a look at the LU factorization, I just mentioned the very brief details about the proof here, how to transform the LU factorizations into the Cholesky factorizations. So this is the LU factorization, right? And then if you take a look at the LU factorizations, what you have here is the L matrix is 1, 1, 1, and then all the things below here are non-zero, right? And this is the LU factorizations. The L matrix in the LU factorization. And then what about the U? The U is the upper right triangular, right? The upper right triangular, you have the U11, and then U12, U22, and then UNN here. And then you also have some non-zero things on the upper right triangular part, right? One way to prove to get such a B and B transpose here is so let me just get one diagonal things here. And then the diagonal things is the D. And then that is a diagonal matrix. And then I just create one diagonal matrix with the help of the diagonal elements in the U. And that is the square root of the diagonal elements here, square root of U11, square root of U22, and then square root of the UNN. And now let's see if I just multiply L and then U, and then in between I insert one I, that is the identity matrix. It will not change the result because this is the identity matrix, right? So let's see what I'm going to do here. So I'm going to factorize the I identity matrix into this way. So I am going to change the identity matrix into D times the D inverse. It doesn't change anything, right? And so with what I have posted on the canvas, you know that the matrix multiplication can be associative, right? So I can combine the order. I can do the multiplication first, these two first, and then these two first, right? So I'm going to do this. So this one is the L times D, and then I would combine them, and then I will also combine the D inverse and then U here. And you can go back to check this. This is the B and this is the C. And you could go back to take a look at the textbooks, the detailed proof there, and it will show you this is the magic happens. The B transpose equals to the C. And that's it. That's how we get the Cholesky factorizations from the LU factorizations. We just insert the D here and then D inverse here. And then this would be the B part, and then this is the B transpose. You can prove this happens. And this is one brief summary about the proof to get the Cholesky factorizations from the LU factorizations. But actually, this is not how we calculate the transpose, the B and then the B transpose here. But the good news here is that because the B and then the B transpose here, we just need to calculate the B elements, the entries in the B, right? So that's how we get 1/2 of the computational cost, because we just need to compute all the elements below here. And then, but for the LU factorizations, you need to compute the elements here, and then the elements here, and then that is the n by n squared. And then n by n squares elements here, you need to calculate. But for here, for the Cholesky's factorizations, you just need to calculate n by n squared and then divided by 2 number of the elements here, and then that's why we have the reductions of the computational cost here. For the Cholesky's factorizations, I have one algorithm here, but I'm going to give you one concrete example here first, because it's easier to understand in this way. So for the examples here, I got the A, matrix A. And then it looks like this: 4, -1, 1, and then -1, and then 4, 2, 5, and then 2, 7, and 1, 2, 7, 5, and then 3.5. And how will we compute this, the factorizations here? We are going to get the Cholesky's factorizations is B times the B transpose. And then B here is the lower triangular one, right? And how could I compute this one? So let's say the B elements, it is just the, because this is the 3x3 matrix, and then the B, it should also be 3x3. And we have, because it is a lower triangular one, and then I'm going to give the name, the element here, it is B11, B21, B31, and then this is B22, B23, and then B33. And then all the things above it is just there, because this is a lower triangular matrix. And so now let's see what happens. So if I do the multiplications here, and I would have B11 0 0, B21 B22 0, and then B31 B21 3, B33, and I multiply the B by its transpose, right? So its transpose, it should be B11 B21 here, and then B31 here, and then 0 0 B22, and then let me see, am I right here? B22 B23, and then B33 here, and this is the transpose of the B, the transpose of B. And let's say, okay, do the multiplication to see what we have for each locations in the matrix. So let's see, what do we have here for the first elements? What do we have? For the first entries, the 1 1, the B11. The B11 is just the first row times the first column. It's just the B11 square, right? And we have the B11 square here. B11 square is the first location. And then what about the first row and the second element? It's just the first row times the second element. And then you will see it is just 0, 0 times 0, these two elements here. And so we just have B11 times the B21 remaining in the result. So that is B11 times the B21. And you will have the similar things for the third row, the first row, third column's elements. And that is this row times this column. And then we just have some things remaining in the final result. That is the B11, B31. And let's say, okay, so I would like to remind you about the A. The A matrix is a symmetric one, right? So if we want to calculate the matrix here, we can use the symmetric property here. So we just need to calculate the things above it, right? And then the things below the diagonal, we can ignore it. So let's just count the things on the diagonal and above the diagonal first. So what about the 2, 2 here? It's the second row and the second column. So here we have second row and then second column, and it has the second column, and then we have, it should be the B21 square, and then top plus the B22 square, right? And what about the second row and then third column? And then it should be this one times the third column. And so this one just zero out the B3 here. We get a 0 here. 0 times the B3 is just a 0. And then so what do we have for this location? We have the B21 times the B31. B21 and then times the B31, and then plus the B22 times the B23. And what's remaining here? We just need to calculate this one. This one is just the third row and the third column, and then we have the B31 square, and then B23 square, and then B33 square. And the remaining things is just a symmetric one, right? So this is just a B11, B21, and they are the symmetric things. Symmetric here, and then I'm not going to write down, because now I'm going to solve for the B11, B12, B21, B31, B22, B23, and B33, and then because it's symmetric, and then this information is redundant. And so I'm going to focus on the information I have here. So let's see, what do we have here? For the B11, it's so easy to solve because the B11 is just the A11, right? A11 equals to the B11 square. And then what's the A11 in our matrix? A11 is just 4, right? So 4 equals to B11 square, and then we got the B11 equals to 2. And then don't forget that in the Cholesky factorizations on the diagonal, it should be positive. It should be the positive element. And so B11 is 2. Let's see what's next. We are going from here and then go to here. This is our next target. So for the B21, because we already know the B11, and then it could be one useful information when we solve for the B21, and then you will see the same things happens here for the third element here, and then we already know the B11, so it can help us to solve for the B31. So our solving map here, the solving map is going from here to here and then to here. So let's see what is the B21. Let's take a look at here. The second element is just the A2, the first row and then second column, and then it equals to the B11 and then B21, right? And this means that the B21 equals to the A12 divided by the B11. And then what is the A12 in this matrix? A12 is the first row, second column, and then that's a -1. So let's copy down. Here we got -1 divided by the B11. B11 is something we have already solved in the step 1, and that is just 2. And so we got this. This is -0.5. And we will do the same things about for the B31. So here, the third elements, we compare the matrix A and the multiplications result we have here. We have the B11 and then times the B31. And we solve for the B31, and we got A13 divided by B11. And what is the A13? A13 and the matrix is just 1. And so I'm going to copy the value down here. And then what about the B11? B11 is from the step 1. The step 1 is 2. The result B11 is 2. So I got 0.5, and that is the A3. Let me see. This is the B31. I have already solved for the B11, B21, and then B31, which means that I already know B11 here, B21 here, B31 here. I already know the first column value after the first round calculations. So next, would you go to here or go to here to compare the values? So we are going from here and then to here because we know the B11, and then we know the B11, so we go to here, right? And then next, what would you choose? This one or this one? This one? Why?
Because you have B21.
You already know the B21, right? Yes, correct. So I'm going to from here to here. So I'm going to compare this one, the B21 square, and then plus the B22 square, and then equals to the A22. And let's compare the value, and then we got the B22 square equals to A22, subtract the B21 square. And if we calculate the B22, we need to take the square root. Take the square root, and so we got A22. What's the A22? A22 is the 4.25. 4.25 square, and then minus the B21 square. There's no square here. It's just the A21, 22, A22. And then subtract the B21 square. B21 square is just the 0.5, -0.5 square. And I'm not going to do the calculations one by one. And then I will just show you the result. It's so easy. It's just a 4.25 subtract the 2.25, right? And then do the square root, and then it's just the 2. And remember that we need to keep the positive value, not the -1 on the diagonal. And now it's quite intuitive that we need to go from here to here, right? And so I'm going to compare this one. This one, you would see that for this one, we already know the value B21, the first column. These are from first column, and then the values, they are the values we already know. And then we also know the B22 values from this from these elements. And then we already know the B22, so we just need to solve for the B23 for this one. If we compare the values here with the A values, and then we are going to solve for the B23. And let's see. Let's compare the value we have here. We have the A, this is the second row, and the third column, and then B21 times the B31, and then they are the values we know, B22 times the B23, and we already know the B22, so we are going to just solve for the B23. And then they equals to B23, subtract the B21, B31, and divided by the B22. And we don't need to take any square root here. And what is the B23? A23. A23 is just the 2.75, 2.75, and then minus the B21. What's the B21? B21 is just the negative 0.5, and then times the B31. We got the B31 here, and then that's another 0.5. 0.5, and then divided by the 2, and this number is just the 1.5. Am I right here? Yes, it's 1.5. You can double check the calculation here. This is 2.75 plus 2.25, and then divided by 2, and then we have a 1.5 here. And so now for the second rounds, we already got the second columns values B22, B23, and that is the values in the B matrix. The B matrix, this is the second column. And now we just need to solve for the last column, last row, the B33. And then with the help of this value here, the result, the multiplications result here. So let's compare the last. So our solving map here is going from here to there. So we are going to solve the last one. The last one, we are going to compare the value. And then this is the value we have on the multiplications result. But they should equals to the A33. So what do we have here? We are going to solve for the B33, and then it equals to the A33, subtract the B31 square plus the B23 square, and then taking the square root. What is the A33 here? A33 is the 3.5, and I'm going to use the 3.5 here, and then subtract the B31, and then it should be the 0.5 square, and then B23. Am I right here? Yes, B23. Where's B23? B23 is the 1.5 square. And doing the subtractions and then using the square root, and then we have at the end, and then B33 equals to 1. So now we have already know all the non-zero elements in the B matrix. So the B matrix looks like this. The B equals to, for the first row, we have 2, and then negative, first column, we have 2, negative 5, 0.5, and then 0.5. And then second column, we have 2, 0.1, 1.5, and then last column, and then we have 1. And the scholastic factorization is just the A equals to B times a B transpose. And that's how we calculate the Cholesky factorization if you are given a positive definite matrix. So it seems that there are a lot of calculation here by hand, but it actually can make the program, if you follow the process here and then you type your program, and then you will find that this factorization is faster than the LU factorizations because it just needs half of the computations. And I have already shown you, I will post it the general algorithm for the Cholesky factorizations on the canvas, but this one is for the handwritten calculations. You get it? Okay. Thank you. So for your final exams, you can memorize the formula, or you can also do it in this way. First show the B and then the B transpose, and then do the multiplications result, and then compare the A1, A2, A11, A12, A13, and so on and so forth. You can do it in this way, or you can memorize the formula. But I prefer doing it this way because the formula is hard to memorize. I would not going for a 4x4 matrix, and I will only go for a 2x2 or 3x3 matrix. So it would not be too horrible. That's it. The factorizations. So you have a good weekend.